Are we good to go? Okay. I'm Terry Camersell here on behalf of Creation Fellowship Santee. We're a group of friends who love to learn about our Creator God and believe that the Bible, when read properly, rules out the possibility of long ages. We met for 10 years at the Creation and Earth History Museum in Santee, California. Then, and online, our goal is to equip believers to defend their faith. You can find over 4 years worth of our virtually there archives by visiting tinyurl.com/CFS archives. That's C like creation, F like fellowship, S like Santee, and the word archives. Tonight, Dr. Jason Lisle ties for our speaker who's presented for us the most times. And you can find links to his other presentations on that archives page. He is also the founder of the Biblical Science Institute. Visit biblicalscienceinstitute.com to find the many articles and resources he has authored on various creation and other biblical topics. But his specialty is astrophysics. And tonight we're thrilled to have him share with us about the brand new discovery he's made based on the James Webb Space Telescope data. If you're watching live and have questions, and you're watching whether you're on Facebook or here in Zoom, you can post your questions into the comments or chat, and we'll ask him when he's done with his presentation. With that, Dr. Lisle, I'll turn it over to you.
Okay, thank you very much for that. I'm delighted to present to you this evening some of the research that I've been doing. I don't often get to do research because I'm in full-time ministry, but every now and then I get to do a little bit of scientific research, and that's always fun. And it's always something that I'm happy to share with others as well. So this will be on how galaxies in the James Webb Space Telescope data suggest a new cosmology, cosmology being the study of the universe as a whole. And it's creation-based cosmology. So that's very exciting and something that is new. And it's something that the article has just been published now in the Answers Research Journal, so you can read about that, how sizes of galaxies in the James Webb Space Telescope data suggest a new cosmology, a cosmology that refutes the Big Bang and is very supportive of creation research and creation ideas about origin. So that's very exciting. And I want to begin by talking a little bit about the history of cosmology, modern cosmology. And that goes back to the early 20th century. Einstein had just developed the theory of relativity, his general theory of relativity. There's two theories of relativity. The special theory, which was earlier, explains how things move explains the weird phenomena that kick in as objects approach the speed of light, length contraction, time dilation, relativity of simultaneity, neat stuff, but it doesn't include the effects of gravity. General relativity is the same theory, but it includes the effect of gravity. And you might think, well, that's a small change, but it makes the math much, much harder. And Einstein, it took him basically 10 years to get from special to general relativity to work out the mathematics of it. And general relativity basically tells us how mass curves space, and then space tells mass how to move. And that's what's responsible for gravity. So mass is what's causing gravity, but gravity is not a force through space, but a curvature of space. And it explains how we can have things like black holes. And that's something that I've written on and something I've studied. I've published in secular peer-reviewed literature on ideas on black holes and how they work in general relativity. And that's cool stuff. In the 1920s, four physicists independently attempted to apply other physicists had attempted to apply Einstein's equations to the entire universe. How do you do that? Because mass curves space, and you have lots of little masses in space, but they thought, what if we just kind of average all that together and get an approximation for Einstein's solution to a universe that has mass in it? And four physicists independently realized that Einstein's equations allow space itself to expand or contract. And those were the first non-static solutions to the entire universe. And that was very interesting. And these four physicists, the mathematical structure that describes the expansion or contraction of space, it's named after the four physicists who discovered it. It's called the Friedmann-Lemaître-Robertson-Walker metric. Metric is the means the math, basically, that describes the expansion of the universe. And so those were the four physicists that discovered it, sometimes just abbreviated FLRW, or sometimes just the last two, the Robertson-Walker metric, which I may use just because the full name is a mouthful. So the Robertson-Walker metric was the metric that describes the expansion of the fabric of space. And you can think of empty space like like a balloon, the surface of a balloon. Now, the surface of a balloon is basically two-dimensional. It has a little bit of thickness, but it's basically two-dimensional. And that represents the three dimensions of our space. And as the balloon is blown up, the fabric expands and so on. And so our universe can be like that. Another discovery was made in the late 1920s by Edwin Hubble. He was an astronomer, and he specialized in measuring distances to galaxies using what are called Cepheid variable stars. Cepheids are pulsating stars. And it turns out there's a relationship between the pulsation period of a Cepheid, which is a few days, and its brightness, its true brightness. And so if you find a Cepheid and you measure its period, you know how bright it really is. And then by measuring how bright it appears, you can measure the distance to that Cepheid, because things that, as a flashlight moves farther away, it looks fainter. It's the same with a Cepheid. And so by measuring Cepheids in galaxies, Hubble was able to measure the distances to a number of nearby galaxies. He also measured the spectral features in these galaxies and found that most of them were redshifted. That is, their light had been shifted from the frequency would have when stationary toward the red end of the spectrum. And normally that would be interpreted as a Doppler shift. Basically, these galaxies are moving away from us and presumably from each other. And because they're moving away, the light gets stretched out to longer frequencies. That doesn't mean the galaxies necessarily look redder. It just means their spectral features have been shifted toward the red end of the spectrum. The overall color of the galaxy doesn't change very much. But the thing that Hubble discovered that was revolutionary is that there is a statistical relationship between the distance to a galaxy and its redshift. And he found that galaxies that are nearby tend to have very low redshifts. A couple of them are even blue shifted. They're moving toward us a little bit. But farther away the galaxy is, the more redshifted it is. And he found that there's basically a linear relationship, that if a galaxy is twice as far away as another galaxy, it's twice as redshifted. Pretty neat. And that worked pretty well. There's some variation there. It wasn't a perfect, it was a straight line on average, but there's some variation there. And he interpreted that as being like a Doppler shift. The galaxies are moving away from us, and the farther away they are, the faster they're moving away from us, as if the entire universe is getting bigger. And these four scientists who had discovered from Einstein's equations that, yes, space can expand, one of them, Lemaitre, realized that Hubble's discovery could be explained in light of an expansion of space. And he published that. And Lemaitre pointed out that if space is expanding, that would explain these redshifts, not because the galaxies are moving through space, but because the space is stretched out as the light travels through it. So as the light is emitted from this galaxy and it's traveling through space, the space is stretched out, and that causes the wavelength of the light to get stretched out. Now, it creates the same effect as a Doppler shift. The galaxies that are farther away are moving faster, but not because they're moving through space, but rather because space is expanding. And so the way this is commonly pictured is if you drew a bunch of little dots on a balloon and you blow up the balloon, expand it, the dots get further away from each other, not because they're moving along the fabric of the balloon, they're stuck where they're at on the balloon, but because the balloon itself is expanding. The fabric of space is expanding. And many astronomers latched onto that. Lemaitre in 1931 said, if the universe is expanding like that, maybe in the past it all went back to a point, and that's when the Big Bang was invented. So Lemaitre invented the Big Bang as a naturalistic way of explaining this expansion, how it got started. Now, almost all astronomers jumped on this and said, yeah, that makes sense, because Einstein's equations allow for an expansion of the fabric of space. And we see this Hubble law. We see galaxies that are farther away are more redshifted than nearby galaxies. So that's probably the explanation. There were a few holdouts. There was a guy named Fritz Zwicky. He came up with the idea that no, galaxies are actually stationary and space is not expanding, but light just kind of loses energy as it travels through space. And that would create a redshift. And that would explain the Hubble law too, because the galaxies that are farthest away, their light has traveled the furthest, it's traveled longest through space, and so it's lost the most energy. Galaxies that are nearby, their light has traveled through space only a little bit, so they've lost a little bit of energy. So that also creates a Hubble law. It just goes to show you that certain observations can have multiple explanations, and it's not obvious immediately which one's right. But Zwiecki's theory, though, one of the problems with Zwiecki's theory is he never came up with a really good explanation for why light should lose energy as it's traveling through empty space. It's not hitting anything. He never came up with a good explanation. And also his model predicted a slight blurring effect for galaxies that are far away. And we now know they're not blurry. So basically, his theory was rejected and the Lemaitre explanation was accepted. And so this, the Robertson-Walker metric, the expansion of space, was thought to be the reason for the Hubble law, for why galaxies that are farther away have a greater redshift than galaxies that are nearby. And frankly, most creation astronomers, including myself, we accepted that because, hey, the equations of Einstein allow for that. They do. And it explains the Hubble law. But just because it explains it doesn't mean it's right. And so this expansion of space has been challenged recently by some of the data that I'm going to present to you. But one of the, there are several weird effects that kick in if space is expanding. And one of those is how do you deal with distances in expanding universe? What's the distance to a galaxy? Now, if a galaxy is really nearby, you know, the Andromeda galaxy is 2.3 million light years away. There's not much wiggle room there because the expansion of space between our galaxy and Andromeda is very small. In fact, Andromeda's motion through space is able to overcome that and move toward us. And so astronomers have different definitions of distance to account for this. And one definition is it's called co-moving distance. Because if a galaxy is far away, it's moving away from us. Its distance, how do you describe its distance? We see this galaxy, which means its light has arrived. Is its distance the distance that it had when it emitted the light? Or its distance today, which presumably is much greater if the light took time to get from there to here using the Einstein synchrony convention? So how do you describe that? And so astronomers came up with what's called co-moving distance. And co-moving distance is basically where you use a coordinate system that expands with the universe. And so in co-moving distances, the galaxies are pretty much stationary. Even though the space between them is expanding, basically your tape measure is expanding too. And so it compensates for that. It treats the universe as if it's static. And the nice thing about co-moving distance is the average density in the universe is constant in co-moving distance. Even you'd think, well, the density in the universe is decreasing because the space is increasing and no new mass comes in to fill it. But if the coordinates expand with the universe, then the average density per volume, because your volume is increasing, remains the same. And so that's called co-moving distance. And depending on the amount of dark matter and dark energy, we can compute the co-moving distance to a galaxy based on its redshift. And let me show you this here. This is indicated by the green curve that you see there. The green curve is the co-moving distance as a function of redshift. Now, this is a logarithmic plot. So a logarithmic plot allows you to express an enormous range of redshifts from 0.001 to 1,000 in this case. And also the distance in gigaparsecs is indicated on the left, also logarithmic. So you got 10 to the -2, then 10 to the 0, which is 1 gigaparsec, 1 billion parsecs, and so on. So that just shows you we can calculate these things. If we know the amount of dark matter and dark energy in the universe, and we think we know those because we can compare distances with nearby galaxies. I won't go into the details of that, but we think we know the amount of dark matter approximately in the universe. And so based on the redshift, we can calculate the co-moving distance. Now, is co-moving distance the distance the galaxy had when the light was emitted? Or is it the distance it's at today when the light's received? It's kind of in between the two is the answer to that. So it's useful in some respects. I should also point out that in addition to expansion of the universe, galaxies can also move through space. And this is important. This is called peculiar velocity. And the way to think about this is imagine instead of dots on a balloon, ants on a balloon, where the ants can move a little bit. But two ants that are far away from each other on the balloon, as the balloon's expanding, those, even if those ants are trying to get toward each other, they'll never meet, because the expansion of the balloon is much faster than their walking speed. So they could never possibly meet. But two ants that are very close together on the balloon, if they're walking toward each other, they could meet, because the expansion of the balloon between them is very small. And so they have a chance of meeting. That explains why some very nearby galaxies are blue shifted, like the Andromeda galaxy. It's actually moving toward us because its peculiar velocity, its motion through space, is able to overcome the expansion of space itself. The expansion of space itself is called the Hubble flow. Peculiar velocities, all peculiar velocities do is add a little bit of randomness to the distance redshift relationship. But once you get to faraway galaxies, the Hubble flow is so great that the peculiar velocity is negligible by comparison. So the Hubble law gets more and more accurate as you go out further into space. And it's not necessarily linear. As you can see in these curves, they curve a little bit. And so the distance and redshift relationship is not exactly linear. It curves a bit. There's another distance that astronomers use called the luminosity distance. And it has to do with the fact that in an expanding space, light gets stretched out, and it gets time. There's a time dilation that kicks in. The number of photons that travel through a section of space is reduced because the space is expanding, so it separates the photons. Basically, it makes objects look fainter than they would if the universe were not expanding and if the galaxies were stationary. So it causes objects to look fainter than they should. Now, normally, if you take a light bulb and you say, that looks pretty bright, and you move it at twice the distance, it will look 1/4 as bright. That's called the inverse square law. And that works great. It works great in space. It works well for nearby galaxies. But for distant galaxies, they look a little bit fainter than they should, according to the inverse square law, because of the expansion of space. It causes the light to look fainter than it would otherwise. And so what astronomers do is, rather than deal with all that complicated math, is basically they say, we're going to define the distance to this distant galaxy, assuming the inverse square law is true, even though we know it isn't. And that'll give us a different distance than its true distance. And that different distance is called the luminosity distance. That's indicated by the red curve. The red curve is the luminosity distance. The green curve is the co-moving distance, and they're different. But the nice thing is there's a relationship, a mathematical relationship between the two. And in fact, if we know the redshift of the galaxy, we can compute its co-moving distance and we can compute its luminosity distance. And if you're looking at brightnesses of galaxies, it's useful to use their luminosity distance, because if a galaxy looks, say, 1/4 as bright, you know it's actually twice as far away in luminosity distance. And then knowing that that's not the true distance, then you convert that to something like co-moving using the mathematical formula that we have. So each distance is useful, but they're different, and they're different because of the expansion of space. The one that's really interesting to me is the white curve. That's called the angular diameter distance. It's cool and weird because it turns out that, as you know, if something looks a particular size and you move it twice as far away, it will look half the size, 1/4 the area, half as wide, half as tall. So the car that's, a mile down the road looks tiny. The car that's right next to you looks big. That's angular diameter. The sun and the moon have the same, approximately, angular diameter. So they look the same size in the sky. Now, in reality, the sun is 400 times the diameter of the moon, but it's also 400 times farther away. And so its angular diameter is the same. So angular diameter, how big something looks. Now, that rule where you move it twice as far away, it looks half as big, that applies to galaxies too, if they're relatively nearby. But because of expansion of space, that rule doesn't work anymore for very distant galaxies that have a very high redshift. And that's why that curve that you see on the bottom there is not a straight line. In fact, it actually turns around at some point and starts getting smaller again. And what that means is there's a maximum angular diameter distance. There's a distance at which galaxies look smallest. And then if you move them further away from that, they start to look bigger, as if they're coming back toward you. So it's weird. So if you see a galaxy that looks pretty big, it could be that it's really close, or it could be that's really far away. That's why there's two solutions. If you take a horizontal line and cut through that bottom, that white curve, there's 2 points where it'll intersect. The galaxy could be close or it could be far away. And it turns out the distance where it turns around, it corresponds to a redshift of about 1.6. And if you get lost, if you got lost in all those details, this is the thing to remember. Galaxies should look smallest at a distance, at a redshift of 1.6. And beyond that, they should start to look bigger again due to the expansion of space, which creates this weird kind of magnification effect. And I'm not going to try to explain the details of why that happens. It comes out in the math, and we all agree that that is true if space is expanding. I've worked out the math myself, and we all agree on that. So that's not disputed. So maybe a better way to think about it is this. If you normally, if you look at a galaxy and then you move it, if you move that galaxy further away, it'll look smaller. If you move it further away, it looks smaller. If you look at, and if the universe were not expanding, that would continue out until forever. The galaxy would continue to look smaller and smaller and smaller with distance. But if space is expanding, then galaxies do look smaller as they get further away until they get to a redshift of 1.6, and then they should start to look bigger again, which is a weird effect because that means galaxies, once you're past a redshift of 1.6, the farther away a galaxy is, the bigger it should look. Weird, I know, it's counterintuitive, but the math says that's what happens in a universe where space is expanding. And that's really interesting because when you look at these galaxies in the James Webb Deep Field, you don't see that. The galaxies that are really far away and really redshifted, and the way they've color schemed it, they are red in this image, just the way they did the color filters, they look smaller than the galaxies that are nearby. So that's weird. And I was not expecting that because, like all other astronomers, almost all other astronomers, I'd assumed that the Friedmann-Lemaitre-Robertson-Walker metric is correct, that space is expanding, and therefore galaxies that are at a redshift greater than 1.6 should start to look larger and larger with increasing distance. I was expecting to see small galaxies obscuring larger galaxies in the background. You don't see that. You don't see that. But, or at least I don't apparently see it. And I thought, man, I need to check this out because this is not what any of us were expecting. And it made me wonder if maybe space is not expanding. So, I mean, the observations indicate what's called the Hubble law. The Hubble law is observed, and it's the fact that galaxies that are farther away from us are moving away from us faster than nearby galaxies. So the entire universe, in terms of the mass distribution of the universe, it's getting bigger. Galaxies are moving away from us and from each other. The standard explanation for that is that space is expanding and the galaxies are carried along with it. So we can imagine empty space represented by this red grid, and as space expands, it carries the galaxies along with them, just like the fabric of a balloon. So the universe starts smaller, and then the fabric of space expands, and galaxies move along with it. But that would create a magnification effect, which we do not see. And so that made me think, well, what if space doesn't expand and the galaxies are just moving through it like this? And that would still generate the Hubble law because the galaxies that are farther away are Doppler shifted because they're moving away. So their light gets Doppler shifted due to a number of factors, including time dilation. Their clocks get slowed. So that slows the frequency of the light, gets redshifted. Okay, so I'm suggesting maybe that's what's happening. And because that won't create the magnification effect. So the standard model, which assumes the Robertson-Walker metric, is that space itself is expanding and it carries the galaxies along with it. I'm proposing what I call the Doppler model, that space is not expanding and the galaxies are just moving away from each other. Farther away, the faster. But and the reason their light is redshifted is it's a simpler Doppler shift. It's not due to stretching of the light through an expanding space. It's just a Doppler shift. And that creates a different that creates different distances, you see. The luminosity distance, if you assume a Doppler model, is slightly greater than if you assume the standard model. The standard model for the luminosity distance, the red curve, whereas the luminosity distance for a Doppler model is the yellow curve. That means things will look a little far away in terms of their brightness, which basically means they'll look slightly fainter. Galaxies will look slightly fainter in the Doppler model for a given redshift than they will in the standard model. There is no co-moving distance in the Doppler model because you don't need it, I should say, because the co-moving distance expands with space, but space isn't expanding in the Doppler model. So I'm just going to call it the Doppler distance. and that represents the true distance to a galaxy when the light was emitted. And if you're using the anisotropic synchrony convention, that's now. If you're using the Einstein synchrony convention, that's a long time ago. You're going to assign a different time coordinate to it, but the distance is the same in terms of the distance relative to redshift. So the Doppler distance is the true distance to that galaxy. If you could take a tape measure and run it that distance, that would be the Doppler distance to that galaxy. But the other thing is the angular diameter distance, which in the standard model turns around at a redshift of 1.6. In the Doppler model, it doesn't. In the Doppler model, the angular diameter distance and the Doppler distance are the same. They're both the blue curve. What that means is this magnification effect that you get in the standard model, you don't see it in the Doppler model. And just for completeness, I also included the tired light model. That's the pink curve. So it has it's similar to co-moving distance, but slightly different. So now if you got lost in the details, zoom back in now. Here's the bottom line. Here's the bottom line. If the standard model is true, and I take a typical galaxy, an average galaxy nearby has a diameter of about 4.5 kiloparsecs, 4.5 thousand parsecs. And we can calculate how big that should look as you move that galaxy to increasing distances, which correspond to increasing redshifts. If the standard model is true, how big that galaxy should look is indicated by the red line. The red line is a 4.5 kiloparsec diameter galaxy. How big its angular diameter is as a function of redshift. And again, it's a logarithmic plot going from 1 out to, I think, 20. And so you can see it gets smaller and smaller until it gets to a redshift of 1.6, and then it starts to get big, and it gets really big. By the time you get out to a redshift of 10 or 20, it looks much bigger than it would at a redshift of 1. On the other hand, if the Doppler model's right, that galaxy should look smaller and smaller as you go to increasing distances, and that's indicated by the yellow curve. And I again included the tired light model. It makes a different prediction. It's indicated by the green curve. The tired light, remember, assumes that the universe is static. Space isn't expanding and galaxies are not moving, but light just loses energy as it travels, and that's what's causing the redshift. And then it occurred to me to, well, at first I thought I need to measure the angular diameter of these galaxies in the James Webb deep field, and then measure their redshifts. But it occurred to me others have done that. And so what I did is I took the results of other astronomers who have published their measured angular sizes of these galaxies and the redshifts of these galaxies to see if they match up with the red curve or the yellow curve or the green curve. And that'll tell us which model is right. Now, but the problem is galaxies, those curves indicate the size, the apparent size, the angular size of a 4.5 kiloparsec galaxy, which is an average galaxy. But some galaxies are bigger than that, and some galaxies are smaller than that. So when we plot these galaxies, there's going to be a range of sizes. But the average size should match the curve of the correct model. So in other words, about half the galaxies should be above the correct curve, and half of them should be below the correct curve. So let's see the results here. So these are the results of several different studies, and I've color-coded them so you can see which study it is. And when you read the paper, which is now published in the ARJ, you can get all the details of those models if you want to track those down. But you can see that, you know, are half the points above the red curve and half below? Well, no, most of the points are below the red curve. So that indicates the standard model is not right. It indicates space is not expanding according to the Friedmann-Lemaitre-Robertson-Walker metric. Are half the points above and below the yellow line? It looks like it. That looks pretty good. And the green line is probably fairly consistent with the data as well, although it doesn't look quite as good as yellow. So this looks encouraging to me. It looks like the Doppler model is the right one. And then it occurred to me, I don't have to guess at the average of those points. I can take all the points in a given redshift between 1 and 2 and average them and actually see what is the average angular diameter of those galaxies and plot the average, and the dots should match up pretty well with the correct curve. So here we go. This is the average size of these galaxies indicated by the yellow dots you see there. And sure enough, they match up very well with the Doppler model, indicating that these galaxies have an average angular diameter that's just a little below 0.3. And then once you get out to a redshift of 10, it's around 0.2 arc seconds. If the standard model were true, which the Big Bang requires, then those points would line up with the red curve. And so they should get really big as you go out to the larger redshifts, but they don't. So this is a really good fit. And there's a little bit of variation because, again, galaxies come in multiple sizes. And there's only a few galaxies in each bin. And so if you have a bin that has an unusually large galaxy, that'll bring the average a little above the correct model. If you have one that's missing a large galaxy, that'll bring the average down a little bit. So we expect a little bit of variation, but I'm amazed at how well the data line up with the Doppler model. And in cosmology, rarely do you get such good agreement between theory and actual observational data. So that, to me, that's mind-blowing. When I saw that curve, I'm like, we're on to something here. We're on to something here. Space is not expanding. Galaxies are moving. The universe is expanding in the sense that the average distance between galaxies is increasing, but they are moving through space. It's not that the fabric of space is expanded. And that's what the Doppler model predicts. And so that's what we see here, the fact that those match up with that curve very well. So I find that very exciting. Now, I have made an assumption. I have made an assumption because those curves are based on a 4.5 kiloparsec galaxy. And I've said that is the average size of a galaxy, which it is for nearby galaxies. We can measure the sizes of galaxies that are very near to us because it doesn't matter which model's right. They all converge once you get to a redshift, below 0.1. They all make the same predictions. So I've assumed that distant galaxies also have the same average size as nearby galaxies. And I find if I assume that and assume that space is not expanding, the data match perfectly. So that's great. But it is an assumption. The way secularists will try to get around this is they'll say, well, it could be that the reason those galaxies look so much smaller than the standard model predicts is not that the standard model is wrong. Heaven forbid that the Big Bang would be wrong. Rather, it's that those galaxies are actually tiny. For whatever reason, galaxies that are really far away are tiny. They're 5 to 10 times smaller than galaxies nearby. And in fact, that's what they're saying, because they've known that these galaxies, because they're assuming the standard model, they're assuming the galaxies should be this big if they're the same size as nearby galaxies. But the fact that they look 10 times smaller means they're actually 10 times smaller than nearby galaxies, you see. But it's because they're assuming the wrong model, I would argue. But that is not a very good explanation for a number of reasons. First of all, there are computer simulations that show how galaxies are supposed to evolve over time. None of them predicted that galaxies start as tiny galaxies and then grow in size. Rather, they're supposed to start as low mass and increase in mass. And that's not what we see here. These galaxies that we see in the James Webb Deep Field are about as massive as nearby galaxies. But if you believe the secular model, they have to be the same mass, and yet for some reason 10 times smaller in each dimension, which means their density is 1,000 times greater than galaxies in our local universe. None of the computer simulations predicted that galaxies should start high mass and then, without increasing mass, somehow increase in size by a factor of 10 in each dimension. So I think that really is an absurd explanation, but that's what they're going to argue. But not only is that absurd because based on the basis of theory, it's absurd on the basis of Occam's razor, because not only does the Doppler model predict the correct size of these, the correct angular size of these galaxies, but it does so at every redshift. From redshift to 1 out to 20, it predicts the correct size. So in order for the standard model to be correct, you'd have to not only argue that galaxies amazingly increase in size for some unknown reason, but that they do so in just the right way to make the Doppler model look right and the standard model look wrong. So in other words, at a redshift of 10, where they're 5 times smaller than they should be. Well, yeah, they're 5 times smaller than nearby galaxies at that distance. But then once you get to a redshift of 1, they're only 2 to 3 times as smaller than nearby galaxies. They'd have to grow in just the right way to make the wrong model look right and the right model look wrong. And so I would suggest that is incompatible with Occam's razor. So I think any good scientist trying to be fair and looking at the data would say, yeah, these data strongly support the Doppler model. They are not consistent with the standard model. They're not. And so this is amazing, because the expansion of space, the Friedman-Lemaître-Robertson-Walker metric has assumed to be it's been assumed to be the correct metric for almost 100 years. And we're now seeing data that it's wrong. That it's wrong. Apparently the Hubble law is caused by galaxies moving through space, not an expansion of space itself. So yes, the universe is expanding, but not space. Rather, the mass in the universe is increasing its distance from each other. But wait, there's more. There's an additional line of evidence that supports the Doppler model and challenges the standard model. Because remember, remember those curves that we plotted earlier that plotted the luminosity distance, for example, which is the distance assuming the inverse square law applies. The standard model and the Doppler model make different predictions on that. Basically, the standard model and the Doppler model make different predictions for how bright a galaxy should be at any given redshift. And the Doppler model predicts that they should be a little bit fainter, and that increases with distance. Let me show you the graph here. So the standard model is indicated in the red curve. That's how bright galaxies should be at a given redshift, assuming that the brightness is the same for distant galaxies as nearby galaxies. That's an assumption. The Doppler model predicts that they should look fainter. If they're actually the same brightness, they should look a little bit fainter if you assume the standard model when computing their luminosity. So that's the white curve. So the red curve is the standard model. The white curve is the Doppler model. The points are the actual data. And you can see there's a downward trend. And the blue curve is the least squares fit. It's the best data fit to the actual data points for the brightest galaxy in each redshift bin. And you can see it has a slope that is negative. The slope seems to match the Doppler model pretty well. And so that's very encouraging. That tells us that not only are the angular sizes of these galaxies consistent with the Doppler model and not with the standard model, but also the brightnesses of these galaxies are consistent with the Doppler model and not with the standard model. So that's cool. That's really neat. And one result of this, one implication, is that galaxies are about the same no matter where they are in the universe. And that was contrary to secular predictions, because in the secular view, as you look out into deep space, you're looking back in time, you're seeing galaxies as they were billions of years ago. And so they ought to look much younger. They ought to be baby galaxies in terms of their mass. But they're not. The mass of these galaxies is the same as nearby galaxies in the same range. We now see that their brightness and their size are also the same if you assume the Doppler model. So that indicates that galaxy evolution doesn't happen. The observational data are perfectly consistent with distant galaxies being very similar to nearby galaxies, as if they were all just spoken into existence by the creator, if you assume that the galaxies are moving through space rather than space being expanded. And the data fit perfectly. So it's really a remarkable thing. Now, if you go through and read the paper in the ARJ, I go through a third test, which is really kind of a combination of these two, their sizes and their luminosities combined into what's called the Tolman test. And the Tolman test, the standard model fails the Tolman test. The Doppler model passes with flying colors. And it's interesting too, because I even looked at some older data that was done with the Hubble Space Telescope, and it too matches the Doppler model and does not match the standard model. And the secular explanation, again, is that galaxies must somehow increase in size and in brightness in just the right way to make the Doppler model look right and the standard model look wrong. But again, I think that's special pleading. I don't think that's a very good argument. So furthermore, I can predict on the basis of the Doppler model what the brightness and average size of distant galaxies at any given redshift should be. And I put those predictions in writing in the paper. And so when James Webb discovers galaxies at even farther distances, which I'm predicting it will, redshifts of 20, 22 maybe, the average brightness should be a little bit less than the standard model predicts by about a magnitude, by about the factor of 2.5, a little more. And the average diameter, the angular diameter of these galaxies should be 0.2 arc seconds. The Big Bang predicts about 10 times that, 2 arc seconds. So there's a huge difference in predictions. And I'm putting that on record. It's now in writing. in the Answers Research Journal, where I can't change it. So that's my prediction, and we'll see what comes to pass in the next few years as the James Webb continues to look even deeper into space. So in summary, the Doppler model, the position that the galaxies are moving through space, and that's what causes the Hubble law, rather than an expansion of space. The angular sizes of distant galaxies are consistent with their redshifts being caused entirely by the Doppler effect and not the Robertson-Walker metric, and that these galaxies are actually the same size as nearby galaxies. And that's exactly the way they should look at that distance if they're just moving through space and space is not expanding. Furthermore, the brightness of these distant galaxies is likewise consistent with the Doppler model and not with the Robertson-Walker metric. So we have two independent lines of data that suggest that space is not expanding, and then that the galaxies are merely moving through a non-expanding space. Furthermore, one of the implications of this is that no substantial galaxy evolution has occurred. Distant galaxies are about the same size and the same brightness as nearby galaxies, and the secularists have already admitted that those distant galaxies are the same mass, the same luminosity, and have the same morphology as nearby galaxies. So there's no dispute on that. So, and this was totally contrary to the Big Bang predictions, where galaxies should start as babies and slowly gain mass and gain structure. They should be clumpy and irregular and then become spirals over time. We don't see that. The distant we have spirals at tremendous distances. They're as massive and now apparently as bright and as large as nearby galaxies. So that's pretty compelling. Another implication is that the Big Bang cannot occur. The Big Bang is dead in the water because it requires an expanding metric. The Big Bang is predicated on the assumption that space is expanding, and if you run it backwards, space was all contained in a point. Now you might think, well, wait a minute. Couldn't space be non-expanding and the galaxies go back to a point? And the answer is no, because galaxies are not moving exactly away from us. They have a little bit of a sideways motion. So, if you take a galaxy that's moving kind of away from us today and you run it back in time, it would miss the Milky Way, you see. Most galaxies would miss each other. They wouldn't go back to a common point. And that's particularly obvious for the very few galaxies like Andromeda that are blue shifted. It's moving toward us today. So if you run the movie backwards, it gets further away. So the galaxies do not go back to a point. The only way to get them back to a point is to assume that space is expanding, and then space goes back to a point, and that means every galaxy goes back to a point because all the space was in the same space, as it were. So the Doppler model is a refutation of the Big Bang. This is devastating against the Big Bang, and I think it's one of the most devastating evidences I've seen. There's already a lot of great evidence against the Big Bang, but this is really compelling because the new model fits the data so perfectly and makes testable predictions about the future. I should also point out the Doppler model is consistent with the ASK model of distant starlight. These are two different models. The Doppler model is designed to explain the redshifts of the galaxies and to calculate their angular size and brightness as a function of redshift. The ASK model, the anisotropic synchrony convention model, is designed to explain how light can get from those galaxies to Earth in the biblical timescale. I fully believe in both models at this point. And one of the things I haven't written on yet, but I will in the near future, is that these two models are not only compatible, they go really well together. When we take a look at the specific math of the Doppler model, it suggests that God not only created the universe in 6 days by anisotropic synchrony convention, but that the way the universe is expanding is by the anisotropic synchrony convention. So that's really exciting as well. So it's at least a confirmation of the ASK model. Doesn't prove it. Each model could be independently true without the other one being true. That's mathematically possible, but it's unlikely considering the way these two dovetail together. So I think that's pretty exciting. We're doing brand new creation research using James Webb Space Telescope data, which is publicly available. I've used the results of other fine astronomers who, although they don't agree with necessarily with my worldview, they've done good work in terms of measuring the angular sizes of these galaxies. I appreciate their work. I appreciate the NASA and all those involved in the James Webb Space Telescope for making this possible. But this really is a revolution in astronomy. I don't think it's an exaggeration to say that it's, in a way, it's like when Copernicus recognized, he wasn't the first, but he was the first to popularize the idea that the planets go around the sun instead of around the Earth. That was revolutionary. This is revolutionary too, because it's, for the first time in nearly 100 years, we're realizing that space does not expand, at least not in the way that we thought. This doesn't preclude absolutely an expansion of space, but it's not expanding according to the Friedmann-Lemaitre-Robertson-Walker metric. And that is a metric that has been assumed for almost 100 years now. So this is brand new evidence that that metric is wrong. And we now have a creation-based model that makes testable predictions about what the James Webb Space Telescope will detect in the future. And if you combine it with the anisotropic synchrony convention, it solves the starlight issue as well. So exciting stuff. Keep informed by checking us out on biblicalscienceinstitute.com. I am going to write up a layman level summary of the Answers Research Journal, probably within the next week, if not the next 2 weeks. So that'll be on there as well. And there's some other good stuff on there too. I had somebody recently challenge the anisotropic synchrony model. He thought he was challenging the model. He was actually challenging the convention. And my latest article is refuting that, Phil Dennis's ideas. He has not done his homework on that issue. And I showed that he's made some mistakes in reasoning. So check that article out as well. And stay posted by checking out our website regularly. And at that point, I will turn it over to questions.
Great. So that was interesting, very interesting. And I think that in our Zoom room, and maybe also I'm assuming on Facebook, we have a very wide level of wide range of understanding. So I think that that's to be expected. And so we have questions that are going to be really easy for you to answer, and then we have some questions that are going to be kind of challenging. So I think that we'll dive in and see how this goes. So first of all, Jess points out, like, some of the people are feeling here. We appreciate that anytime you say, so basically that means that's when a lot of the people are going to go, oh, this is where I can understand. So like that. And then if somebody couldn't explain exactly everything that you said, but the takeaway maybe would be the fabric of space is not expanding, even though the galaxies are moving apart. Is that like a great summary? Like,
you got it. Yeah.
Okay. And then they can post, if they say that to their friends, they can say, now go read this article or watch this video, and he'll explain the rest. So,
yeah.
Okay. Yeah. So given that, then let's talk about the Bible Bible verses that say that God's stretching out the heavens. How does that still fit?
It still fits because the average distance between galaxies is increasing. The Hubble law is true. It's just a question of what's the mechanism. Is the fabric of space expanding and the galaxies are going along for the ride? Apparently not. The galaxies are moving away from each other, though. So that is an expansion. God's expanding the mass in the universe without expanding the fabric of space, apparently.
Okay. And okay, so next question, what is a parsec?
Yeah, a parsec is a unit of distance that's commonly used in astronomy. It's equal to 3.26 light years, and a light year is 5.88 trillion miles. So you could convert it to miles if you wanted to. There's the formula. 5.88 trillion times 3.26. That's how many miles is in one parsec.
Okay, that helps. And is there dark matter, and how do we know?
Yeah, I believe that the evidence for dark matter is extremely compelling. Basically, dark matter is anything in space that we cannot see. We can't see its light or its shadow, but we know it's there because it's pulling gravitationally on something that we can see. And so the way stars orbit the core of their galaxy, we know there's more mass there than can be accounted for by simply these stars themselves and dust and gas. There's more mass there because their orbital periods are faster than they would be if there was just gas and dust. The stars would be orbiting slower. Furthermore, the way light bends when it goes around a galaxy is determined by the amount of mass in that galaxy. And by measuring the bending of light, what's called gravitational lensing, we can estimate the mass that's in that galaxy. And sure enough, it's 10 times larger than the visible mass in that galaxy. So there's 10 times more dark matter in the universe than visible matter. The only alternative is that our understanding of gravity is wrong. And that is a possibility, but the way we've dealt with gravity, our predictions based on gravity have been so successful in getting spacecraft from one place to the next and so on. We think it's more likely that there's some kind of mass that's not been detected yet then that our understanding of gravity is wrong. But theoretically, either is possible.
Okay. Um, Before we move on, let's revisit the parsec answer, because somebody would like to know how long it would take the Enterprise to go 1 parsec.
The speeds in Star Trek are not very self-consistent. So it'll depend on which book you ask. And they changed the warp scale between the original series and the Next Generation anyway. So I don't know how long it takes. Somebody's done the math. You can probably do the math with Voyager, because Voyager's in the Delta Quadrant, and it's supposed to take 70 years at maximum warp to get to Earth. And our galaxy is 80,000 light years in diameter, which would be what, 20 kiloparsecs, something like that. So that'll give you a basis for an approximation anyway, but I don't know the number.
I was being funny anyway. Yeah,
I'm sure.
Okay.
Um, Everybody needs some kind of reference to put this into context. So, have you been consulting other creation astronomers on this theory?
Yes, via the peer-reviewed literature. I had 3 creation astronomers review my work in the Answers Research Journal. I don't know who they are. I know who I recommended, but they don't have to take my advice in terms of who they recommend. But all 3 of them thought that this was a good paper, and they made, no, I take it back. One of them thought that it needed to be that there needed to be some adjustments on it. But I actually made most of the adjustments he recommended anyway, and the other 2 thought it was amazing. So, and they recommended publication. So, yeah.
More specifically, Steve would like to know if Hugh Ross has had any review of it.
Well, the paper came out yesterday, so I doubt Hugh Ross has even read it yet. I hope he does. I'd love to see what his reaction to it is. My prediction is what Hugh Ross will say is whatever the secularists say, because his beliefs about the universe are basically whatever the secular beliefs are, but God did it. To be perfectly honest.
Okay. All right. Now we're going to get into some more challenging questions. So, what about considering the cosmic distance ladder?
That still works. It's just that the last 2 rungs on the ladder, where you're dealing with these enormous distances, at that point, your model matters, and what type of distance you're talking about matters. Is it a luminosity distance? Is it a co-moving distance? Is it a light travel time distance? Is it an angular diameter distance? And there's multiple definitions for distance. And the reason we don't worry about those different definitions for nearby stuff is for nearby stuff, they're all the same. For the Andromeda Galaxy, it's co-moving distance, luminosity distance, angular diameter distance, light travel time distance are all equal. They're all the same within a small percentage. But for large distances, you have to know which one you're dealing with, and it will make a difference as to which model you're using. So if you go back and look at those curves, the Doppler model basically predicts that galaxies at a given redshift are slightly further away if you compare the Doppler distance to the co-moving distance. Actually, I forget which way it is. You'll have to take a look at those curves. I think the Doppler distance is actually, they're a little closer than they are. It's not a huge difference, but it's enough that it makes different predictions in terms of how big the galaxies should appear and how bright they should appear.
Okay. What is causing the galaxies to expand through non-expanding space?
That's a very good question. I would have to say that my guess would be that God imparted momentum to those galaxies at the very beginning, that he gave them that momentum so that the mass in the universe would not collapse in on itself. So it's a question of stability. The way to think about it, instead of dots on a balloon, think of billiard balls on a table right after you crack the deck, and they're all moving away. The ones that are moving farthest away are moving away fastest. Now, that doesn't mean that God started all the galaxies at the same point, because we know that if you run them back, they would miss each other. But it gives you a rough idea of what's going on. Apparently, God created the galaxies pretty close to where they are today, but he gave the ones that are farthest away from us the most velocity relative to us. Now, of course, from their perspective, we're moving fast in the other direction. So it's all relative. But basically, it's just the initial momentum that God gave those galaxies, perhaps to make the universe more stable.
That's interesting. Um, so using the model where distant galaxies look big again, how would one know if a galaxy was close by or if it was very distant looking large?
Yeah, good question. From just looking at it, you can't tell. The answer is redshift. The redshift of the distant galaxy would be enormous. The redshift of the nearby galaxy would be small, and their brightnesses would be different as well, but their sizes could be the same.
Okay, so going based on that, what is causing the redshift if space is not expanding?
Doppler shift, the Doppler effect. Okay, so something moves away, the light waves get stretched out from one peak to the next. And so, and there's a time dilation effect as well that kicks in. Clocks are ticking slower, so the frequency of the light is slowed down. So it's just ordinary Doppler effect. When the thing moves toward you, it gets blue shifted. If it moves away from you, it's red shifted.
And how does this model affect our understanding of the age of the universe?
It means the Big Bang's wrong. So it means those that hold to the billions of years no longer have a viable model, at least not one that fits the data. They do not have a model that fits the data. We do. The Doppler model in itself does not require a young universe. It doesn't. It's just explaining it's explaining redshift, what's causing it, and it allows you to calculate the angular diameter and brightness of a galaxy for a given redshift. But it's certainly compatible with the anisotropic synchrony model, the ASK model, in which light reaches Earth immediately. So the Doppler model, being consistent with the ASK model, basically is very compatible with a young universe. And the fact that the Doppler model shows that galaxies do not evolve at all indicates that they're not billions of years old. So I think it's at least consistent with a very young universe. It doesn't prove it, but it's consistent with it.
So, in other words, people who understand the Bible and read it properly are not changed by this in their view of how old the Earth is.
Right. Which should always be the case.
Right. And okay, so a follow-up question from Eli, who asked the question about the galaxies, what is causing them to expand through non-expanding space. He's asking what would be the material reason.
What would be the material reason?
Yeah, I'm not sure if
it's just whatever initial momentum they had when they were created. God apparently created those galaxies in motion. And the galaxies that God chose to make farthest away from our galaxy, he gave them the fastest speed. He gave them the most motion. It's like asking what's the cause of Earth's rotation? Well, what God ultimately is. And the fact that the momentum is conserved, the Earth will continue to rotate because there's nothing to slow. I mean, the moon's slowing it down a little bit, but not very much. So there's nothing to slow the galaxy. There's a mutual gravity which could slow them slightly, but they're continuing to move at that speed because that's the speed God started them with. So that's what's causing that. There's no other answer I can give other than that's apparently the way God initially created the universe, and God is maintaining that that motion in accordance with what we'd call the laws of nature, which is the ordinary way God upholds his creation.
Okay. Is everything expanding on a plane or in a sphere?
It's a three-dimensional expansion. So more like a sphere. So there are galaxies that are above us are moving away from us that way. Galaxies that are below us are moving away from us that way. Galaxies that are that way are moving that way. Galaxies that are over here are moving that way, this way, that way. It's a three-dimensional expansion.
Okay, and then there's some conversation about the Doppler effect. That maybe you can explain this, because if other people maybe are watching and not reading the whole chat, then they might have the same question. So I'll go ahead and ask. So somebody is asking if the Doppler effect was only regarding sounds, and if there's no sound in space, how does the Doppler effect work in space?
Gotcha. I'm glad you asked that. I should clarify. The Doppler effect works with light as well as with sound. It works with any wave phenomenon. If the thing is moving away from you, the wavelength will be stretched out. And so it will be shifted to longer wavelengths. That works with sound. And it's very easy to detect with sound because the speed of sound is relatively slow. The speed of sound is only about 700 miles per hour. And so a car that zooms by you at 70 miles per hour, he's going 10% the speed of sound, right? So, so you can hear the change in pitch. With light travels at 186,000 miles per second. And so something has to be moving really fast to see a Doppler shift with light, but light will Doppler shift the same way sound does, and light can travel through the vacuum of space. So theoretically, if you had, let's say you had a flashlight that emitted a yellow beam of light, if I could move that away at a high fraction of the speed of light, that flashlight would look red because the wavelengths would be stretched out. If I could take that same flashlight, which is actually yellow, and move it toward you at very close to the speed of light, the flashlight would look blue. The waves would be compressed in the direction of motion. So now the effect is harder to see with light because of the way our eyes work. Our eyes are synthesizers, our ears are analyzers. So we can detect frequency. With your eyes, you can't do that. So you need special equipment to detect the Doppler shift with light. You need a spectroscope, and that will allow you to measure the shift of the spectral lines toward the blue or toward the red. But it works perfectly well with light and in space.
Okay, let's get back to an easier question. And Jess would like to know, how long did you research this discovery?
I've had the idea for a long time. When the first images came out, I thought that's weird that they don't look bigger, that the farther galaxies don't look bigger than the nearby ones, because I had assumed the Robertson-Walker metric. So July 2022, when I first saw these images, is when I began to suspect something was wrong. And I was chatting with a friend of mine last year, 2023, late summer, and I thought I need to go through and do this calculation. And I had some downtime in November, December last year where I wasn't really doing much speaking, and that gave me the time, because it takes time to do these calculations. And frankly, I'm a little bit rusty. I've been out of grad school for 20 years, and I don't do astrophysics every day because I'm doing other things. But November is when I really started working in earnest on this, and it didn't take me very long to see the pattern there. Once I got the data, I had to figure out how to get the data from these papers that other people published, and some of them put their data online. And thank you for doing that, because that made it easy for me to download that. They made it publicly available, and then I could just plot the points. And then I had to work out the math of how the Robertson-Walker metric would differ in terms of the angular diameter from a simple Doppler model. So it took a good month to work through that, and then another month to follow up. So November, December is when I was really working on this. And then I wrote up the paper in January, and then it was relatively straightforward going from there. Had it sent in for peer review, got comments back from the peer reviewers, and incorporated those. They made some good suggestions, and I incorporated those into the paper. And then it just took them a while to get it published. So, because there's other papers in the process as well.
Yeah. Well, we posted a link to the paper in the on Facebook. I'm keeping track of Facebook. So but we posted it in the comments there. We also posted it in the chat here on Zoom so people can find that. And then and that last question is well, maybe two. So Linda would like to know, does the paper show all the math?
Yes, it does.
Okay.
Yep.
And then do you expect it to be published in any secular publications?
Well, no, usually only publish something in one journal. You don't usually publish it in others. And I'm fairly confident that this would have passed peer review even in a secular journal. I probably would have removed some of the specific creation implications, but in terms of challenging the Big Bang, it's starting to become cool again to challenge the Big Bang. It was when it first came out in 1930s, when the Big Bang was first, everybody was challenging it. And then it kind of settled into, well, that's the right one. But now there have been others who have been promoting the tired light model in light of these James Webb Space Telescope data. That's really one of the things that encouraged me to pursue this. There's at least two other papers, and I referenced them in my technical article. I referenced some other folks that are trying the tired light model and pointing, because it's not as good a fit to the data as the Doppler model, but it's better than the standard model. The tired light model fits the angular size data, because if you remember that green line at the bottom, it also shows that galaxies decrease in size as you go to greater redshifts, as the Doppler model does. It's got a little bit too low to fit the data, but it's closer than the standard model. So, and those papers were published in a standard secular journal. So I hope that even some secular astronomers latch onto this and realize they now have an alternative to the Big Bang. They don't have to accept creation just because of this. The Doppler model doesn't immediately require biblical creation. It's just compatible with it. And that's one of the things that's neat about it. So I'm hoping that even some secularists will start considering this. But if they want to read about it, they'll have to read about it in creation literature.
Yes. And I mean, so to that end, do you think that they will start working on a new model? Like what do you think the reaction will be to this?
Some people already have, for the same reason, not as a result of my research, but as a result of the small sizes of these galaxies that led up to it. There's at least two, as far as I can tell, there's secular astronomers that are proposing alternatives to the Big Bang. And one of them's proposing a tired light model. The other one's proposing a combination of tired light and the standard model, 50-50. And what that'll do is it'll double the age of the universe. And so if you've heard, and I don't think that'll catch on, but if you've heard these media claims, hey, astronomers now think the universe, whatever, 28 billion years old instead of 14 billion, that's this one small group of astronomers that's trying to combine the tired light model with the standard model. So they're saying the universe is partly expanding and light loses energy as well. But the problem with that, I think, is Occam's razor. You're trying to combine two different mechanisms to explain it, and that's not good in science. Usually, if one mechanism will do, why use two? So I don't think that's going to catch on. But I'd love to see some secular astronomers read my paper and consider a Doppler model. I think some will. I think some will. They won't accept creation, but they'll try a Doppler model and they'll try a secular version of the Doppler model.
I guess when you don't have an unchanging standard, time is very fluctuating.
True.
So James wants to know if this is a good way to remember it. Galaxy storyline, same size, same shine.
Yeah. Yeah. In the Doppler model, they're the same size and they're the same size and same brightness as nearby galaxies. In the secular model, they're almost as bright, but not quite. And their sizes are much smaller. And there's no real mechanism to explain that. The only reason they believe that is because they're assuming an expanding space. And so they're assuming this magnification effect is there and that we're not seeing it because the galaxies are actually tiny.
Okay, so what I'm hearing from you in total is it's a great time to be a creation scientist.
It always is, but it's especially of late. Yeah, it's especially of late because we now have a quantitative countermodel to the Big Bang, one that fits the data better than the Big Bang. I mean, if you're just looking at it just from a scientific approach, laying as much of your presuppositions aside as you can, and I realize you can't completely do that, but just looking at the two models, mine fits the data. The Big Bang doesn't.
Yeah.
And mine makes predictions, and we'll see what happens with the new James Webb Space Telescope data, because my predictions are 10 times different from the Big Bang predictions. I'm predicting that the farthest galaxies they find will have an average diameter of 0.2 arc seconds, whereas the Big Bang would predict 2 arc seconds. So it's a huge difference.
Okay, and then you're going to be rewriting your article in a layman's level, which a lot of people here are like. So tell everybody where they can find that and where they can find all the rest of your work.
It'll be on our website, the biblicalscienceinstitute.com. And that's the name of it, biblicalscienceinstitute.com. And just pay attention, because probably within the next week or the next 2 weeks, I intend to write a layman summary of what all this means, why it's important, that kind of stuff. Because I went into I know this group, I know there's some fellow nerds here, so I went into a little more detail for you guys. But if you're saying, yeah, I kind of got lost in the math, that's what the layman summary will be for. And hopefully it'll make a lot of sense. I think anyone can understand the takeaway that galaxies are moving through space rather than space is not expanding, just carrying the galaxies along. Galaxies are moving through it. And that makes different, and the mathematics of that makes different predictions about how big galaxies should look at a distance. And ours predicts that distant galaxies are the same size as nearby ones, and that's exactly how big they look. So whereas the Big Bang would require them to be much smaller and somehow grow in size without growing in mass, which no one predicted. So that's the bottom line. We have a model that makes successful predictions that's compatible with a young universe.
Okay, biblicalscienceinstitute.com. And we are Creation Fellowship Santee, and you can email us at creationfellowshipsantee@gmail.com to get on our list, so that you'll get emails for our upcoming speakers. We'll be off next week, but in 2 weeks, we're looking forward to having David Reeves come and give us an update on all of the exciting new things that are going on with his Wonder Center in Tennessee. So with that, we're going to go ahead and sign off the recording and live stream.